Okay, so good morning, everybody. We have right now 8 people attending, so probably a few more will enter in the next few minutes. But in any case, we will start right now with the materials for today. We have a lot of things to talk about today, so let's get it started. Let me share here. Okay. Today we will be covering 2 main topics: the text editors in Unix, Linux environments, and how you can use the software available on an HPC cluster, which is something very, very particular for high performance computing clusters. And the 3 venues for installing, for accessing software, usually scientific software, compilers, libraries, that sort of thing, inside a HPC cluster. Let's start with this. In your personal computer, you probably are familiar with what are called word processors, like Microsoft Word, LibreOffice, Pages on Macs. So there are software for writing, for example, letters, eventually writing a paper if you are not using LaTeX, for example. Some people, depending on the area, some people prefer LaTeX, especially physics, mathematics, and probably chemistry. But some people in engineering, in other areas, they write their papers in Word or some a word processor. We are here talking about something completely different. Those are programs that are designed only to write text files, no format, no change of fonts. It's just the text, it's just the content. The content of the file are just a set of characters, as simple as that. And they're very important to use in high performance computing cluster, because all the time you are writing input files, so the files that the code will use to create a simulation, or the submission scripts. This is something that we will be discussing next week, submission scripts, or simply accessing or collecting data from the output, putting that on a table or another text file. So text editors are widely used. They are completely different from a word processor. No formatting is involved here. It's just the file. It's just the text. Now, in our previous lesson, we learned about a few comments for reading the file, just for opening the file for you to read as a human. And those commands, for example, were cat, more, less. This kind of commands only allow you to read the file. You cannot modify it. However, when you need to modify the file, you need to use a text editor. We will be concentrated today on 3 main editors that are widely used in Linux, and more particular, they are widely used in, okay, Kylie, I think Daniel can share with you or share with everybody the links for the YouTube videos. I think that we have uploaded some of them. Correct me. Yes. Okay. Okay. So we are talking about three main editors in Unix Linux environments. Editors that only rely on the terminal. So we are not talking about something that uses graphic user interface like Windows, things like that. Some people, however, could eventually use those uh, graphic user interface editors or use indirect ways for editing files if they prefer to do so. For example, the VS Code could allow you to edit the files and transfer those files to the cluster. There are some other ways to do things, but in general, we will be discussing only text editors, the terminal-based. There are a few notes to be made here before we explore the three editors that we will be covering today. In Windows machines, you probably have like a Windows key that is close to the spacebar. On Macs, they are slightly different. So they have on the left side of the spacebar, they have like command that has a very particular symbol. The option after that on the left, the control on the left, and on top of that, the chip. All those keys are very important when you are using a text editor because they allow you to change the behavior of the editor just by pressing those or combination of those keys. So it's important to understand that sometimes when you see something like meta in Windows machines, that means the Windows key. On Linux and on Macs, they need to be replaced, for example, with the escape key. So there are different behaviors. And here is a description of what the different options are or how those text editors that we will be showing today map those keys, named with those traditional names, into the modern keyboards. So, as I told you, we will be discussing a little bit about three main editors. The easiest of them is this Nano here. And we will be exploring a little bit about this. Okay. Oh, yes, well, I can. Let me see. Okay. That's the link to this material that you are looking right now in front of you. So the easiest of those editors is Nano. It's very easy to use. They have like a bottom bar that give you clues on the easiest commands to execute. This is probably the first text editor that a new user will select first. As the time goes on and you need a more powerful editor, people will start deciding, will exploring, and eventually decide if they want to use Vim or VI. which is a more powerful editor. They add a lot of capabilities that are completely lacking on Nano, that could accelerate your editing under some circumstances. We will see a little bit of that. Or Emacs, which is another very popular editor. But assuming that this is the first time that you will be dealing with and you are learning command line interface and all that, you select Nano. This is the first editor that you will select. The way you open a file for editing is just with the word Nano and the name of the file. By the way, Nano is just like kind of a joke. Is the name comes from a previous editor of the old times from the 80s that was very popular in Unix systems. That is called Pico. So after Pico, it came Nano. That predates even Linux itself. So now, I am deciding here that on a text editor, you need to know at least 4 or 5 skills, minimal skills, or atomic skills. And that's what I'm describing here in this document. I will have to move this relatively quickly, and you can read the material on your own. But the idea is, for each editor, I am describing here how you move around the file, which is trivial in Nano because you use the arrow keys, you move up, down, right, left. That's it. And there are a few keys here for moving to the top of a file, and I will demonstrate that for at least for Nano. I will be demonstrating all this. So to move into the beginning of the file and the end of the file, which is something that you often use when you open, let's say, the output of a simulation. On some codes, what you get are thousands of lines. And sometimes what you want is the header, the very beginning of the execution, where you know, okay, if the conditions were right, the temperature was correct, which are the characteristics at the beginning of the run. And sometimes all that you want to see quickly is the very end of the execution, if the execution was correct, if the energies were kept constant, if that is the case, or if you produce meaningful results somehow. And after, yes, you can dig into more details about the execution, if the execution was makes sense from physical, chemical, or biological reasons. Okay, that's the first skill, how you move around the file, how you copy, cut, and paste portions of text from one place to another in the text file. How you search for a specific word, for example. And that's it. This is the very minimum. Opening the file, moving around, copy and paste, and search. If you know that, you can, even slowly, but you can navigate the file, you can do all that is important. Probably there are more efficient ways of doing certain things. For example, to move to a very specific line. We will learn about that. And how you access more information about this editor. So that the reference. So here you will see, okay, those are all the different options. In the case of Nano, the different options are by pressing the control key and something else. The control key and some other key that will activate this behavior. So they are described here. I think this is I don't think this is exhaustive. Then I just pick the list of some of them, of the options. Okay, this is one editor, and this is the editor that I will demonstrate for a few things before moving to the next topic. But I will also have here, in more length, the other two editors. Emacs, which is also very, very popular. And there is both the text, the terminal version of Emacs, and sometimes there, especially if you are using on your own computer, there are also graphic user interface, so versions with icons and buttons and all that. So the advantage of Emacs is that it's far more powerful than Nano. You can do things that are simply not possible, like cutting in blocks or copying them. That's something that is obscure. Imagine that you have a file with multiple columns. And one of the tasks is you have one column and you want to swap it or move it to another location. A column of not just the lines, just a particular column. So that's something that Nano doesn't allow. As far as I know, Nano, you cannot do that. But you can do that very easily with Emacs or VI or Vim. So again, the skills that what you need to know is to opening and closing the editor. So that's one thing. So now closing is not so trivial as it is on Nano, which is they give you the control key for exiting the Nano. In this case, there are a few key combinations for saving or leaving the editor, which are here. Control X, S to save and exit, so saving to the hard drive and exit. And here is the description of how exactly you're supposed to press the keys. It's Control S, Control X, you keep the control press, and S. How you move around. So again, in the case of Emacs, you can use the arrow keys up and down, that's okay. You move the very beginning of the file with the less than and the meta key or the Windows key, you move to the very beginning of the file, and you move to the end of the file with the meta key and greater than. So, and you can go to a very specific line in the text file with Control G, Control G. So that's another thing. So how you move around, how you copy, cut, and paste. So in that case, there is an option to select a portion of the text with Control and space, and after you move and after you cut, or you copy and paste. And I think I will only demonstrate this for real in the case of Nano. Eventually, with the case of Nano, I will skip in the demonstration Emacs because the time, I think the time is better spent on the software side, which is a big chunk for today. So I just describing this, but I will not demonstrate it anymore. And the reference here that I'm pasting is kind of like the official reference card for Emacs, where you have all the combinations. Some of those combinations can relatively be complex. You see, there are some that require multiple fingers, so you need to have at least a full hand of fingers to type in all those commands. Okay, when you see the M, when you see the C here, the uppercase C in this reference card, it means the control key. When you see the M here, is the meta key, which is the Windows key on Windows machines. Okay, and the third editor, which is probably the most complex editor to use, but also very powerful. So there is a balance here between easy facility of usage and the complexity and power that you get from the editor. In the case of Vim or VI, Vim is like an improved version of VI. The good thing about VI is that you have some assurance that on any Unix system, you should have at least VI, at least the old version of that. So the VI is there. So not necessarily Emacs is there, not necessarily Nano will be there, but VI as it is part of the POSIX specification, something technical in the in Unix systems. A system that complies with POSIX will have VI there. So that's one of the advantages. The disadvantage is that it's a modal sort of editor. So you need to switch with the special keys between command mode, edit mode. So the operation is different. So beginners could become confused on how you operate with VI. So the first thing that you need to know is how to leave that VI. So you, by chance, you enter into the on this editor, and you struggle to leave from the editor because nothing will work. It tries to press key, or you could press keys around, and nothing happens. So it started making gibberish on your text. So the way you leave the editor, you exit, and after you learn a little bit more and you learn how to use it, how you leave the editor in case of panic is you press the escape key, you put the colon, Q, and exclamation mark. That's how you leave the editor. Or if you want to save whatever you wrote and you know what you are doing, you press the S key and the colon and X. It will save and leave. Now, moving around, it depends on which version you are using. If you're using the old-fashioned VI, that code, VI, was written in a time when the arrow keys didn't exist on keyboards. So we are talking about the late 70s, 80s, probably, where those arrow keys that you have on your left and the bottom left or bottom right of your keyboard were still not present. So the way you move around is being in the command mode, so mode when you enter, and you use the H, J, K, and L. So the 4 keys that you see, all those 4 keys that are there, they are in line. They are on the right side of kind of a right side of the keyboard, and those are used for moving around in the text. So if you are using the Vim, the improved version of VI, yes, you can use the arrow keys and it will understand those arrow keys as usual. So that is one thing to know. So you copy, cut, and paste. Again, you need to change modes. I will describe that in a minute. And with that, you can copy or you can delete and keep in memory and paste that text below. That is, the operation is different, and I will demonstrate that. That's. And here I found a very beautiful reference card for VI, so with all the commands and a very kind of infographic way how you can use those to move like to the right, to the left, one word up, one word to the right, one word to the left, or one character to the right, or the whole thing. So all those things will show you here if you want to move to the next character with all the old keys, or the entire word, or the entire line, or to the bottom of the and a few other things that you can do for searching, for example. I think here, search. For searching, you use the slash. We will go into that in a demonstration. So you have it here on your own. You can read the 4 skills for each editor. Do something for you. Try to explore first Nano, explore a little bit Emacs, and explore Vim, and try to figure out which editor you think you feel better, you want to explore more. If you are happy with Nano and you don't want to learn anything else, keep it as simple as that. Nano will do that. So now, for the exercises, and I will give you a few minutes to explore this while I am also showing some other things here. This is the challenge. I am writing a code. This code is written in C. It's very short, but it's also nice. That will produce a fractal, a well-known fractal. So this is the idea. Write this code. The reason why I select this is because you notice, and this is something that happens a lot in programming, that you have some patterns or some things that are repeated somehow, that where you can try to, instead of typing that entirely, what you can do is to, when you start writing this file, when you reach this point, you just copy this section here and try to make a copy here. So duplicate the line here and just editing what changes. Doing the same here and introducing the small change. That at least give you a feeling of what you need to do to copy sections of text and paste those below or somewhere else and to write this. Another thing for which I am using this kind of exercise is that on some editors, in particular Vim or Emacs, they offer you coloring, text coloring for well-known formats of text files. So for example, if you are working with code in C, it will understand which are the words in the language and which are the symbols that are used, for example, for opening a block, closing a block, and the editor will color your code, which is very handy when you are developing code. And sometimes some of those editors also include checkers, where you get some warnings when you are forgetting to put some of those symbols, or you are not closing correctly the brackets, for example. They will map you, or they will highlight which bracket is closing which. All those niceties are probably not very relevant for someone who is sporadically editing a file, but they are really important when you are into the business of writing code or editing the code from someone else. So that's why I select an exercise with a code here, the programming language. Another challenge here, in addition to that, is try to write, at least for BI, to try to use the old-fashioned keys. It's something to force you in case by chance you end up working on a cluster without Vim. You know what to do. You know how to move around. In our clusters, in Thornyflat, in Dolly Sots, we always have Vim there, so it's okay, and it's not mandatory. When you finish with this, writing this code, you save it, you compile it. You don't need to load modules. You don't need any special software that we will see in a minute. You just save the file with the extension C, and this is the command line to compile the code, and this is the line to execute, and you will see the Sierpinski triangle, which is famous. You can search on internet, or you can write the code, execute it, and check on your own how it looks like. This is cool. Now, there is another exercise that I will do. Originally, it was written a long time ago. I suggest to use the tricks for getting into the cluster with X11 forward. What I will be doing is demonstrating you how you can execute this code using the desktop, the virtual desktop, which is probably much better, easier. Now that we have Open on Demand, and we can create a desktop for Open on Demand and execute this. And so this is the last part that this is another section where I am showing you how to edit the file, how to introduce a few changes to the file for generating another fractal. That's and here I have a big file, and I would like to do this is from the COVID time, so then they have like all the cases around the world. Okay, so there's a big file, and then the reason for I choose this is because the challenge is to use the search and the movement capabilities of the editor. So the line has like, I don't know, it's a few million lines. So of course you cannot traverse all those million lines just with the arrow keys. So there are the challenge is how to go to the beginning of the file, how to go to the end of the file, and how to move or search for a specific place or a country, for example. And a country will position you there to search for the cases on a given time in the file. And here is just some historical comments on why those keys were missing in the why the original VI is not working with the arrow keys. Okay, that's it. Now I will demonstrate this for real, and I will be doing it here. So you can use the terminal just for me to be easy to demonstrate this. Or make it easy. I will be using the terminal inside Open on Demand, and I will give you here, if you want to do it this way, I will also copy here the link for Open on Demand. So only you just need to click there. You will open in Open on Demand, and I will be showing you this here. Okay. So remember that Wednesday during the first lesson, I show you how you can clone this. So if you execute this, I will demonstrate this. All that you need to do is git clone this, and it will recreate the repository with examples, with the materials that I'm using here for demonstration. So I am copying and pasting. In this case, what you need to do is to copy that line and execute that in the terminal of the cluster. So that's, and I will be deleting that. Okay, so once you have that, there is a folder called workshop hands-on. And introduction HPC, and now we will go into the editors, which is 4 here. Okay, let's explore a little bit Nano here. And let me see how I plan to do that. Okay. Nano. This is how you open the editor. You see, you will see here on top of on the top first line, Nano, the version, and the file that you are editing. That's convenient. And on the bottom, you see the lines, a couple of lines with the clues for the different commands that you could possibly use here. So if you want to exit the editor, it's just Control X, and all that you have to do is to press Control, keep the Control pressed, the Control key pressed, and press the X. So that's how that works. Again, in this editor, you can move up and down with your arrow keys. And you move, in the case of a Mac, the meta key doesn't exist on itself. In the Windows, in Windows machines, on Windows keyboards, is the symbol for the Windows. That's the replacement for the meta key. In my case, with a Mac, what I do is to press the escape button. For example, you see the instructions here for going to the end of the file. You go here. And so, okay, so you open the file, and I show you that, and you leave the editor with Control X. That's what we learned. Moving around, I told you, you can use the arrow keys, they work, and you use the meta key with backslash for the beginning of the file, and the meta key and a slash for the end of the file. So that's what I'm doing here. So if I position myself here, I can go to the very beginning of the file with escape backslash, and I can go to the end of the file with escape slash, which is, well, it's not that hard when the file is small, but if the file is big, like this one, well, you have to execute this and to download this. Let me see if this works. No. Oh, it's no longer. No. Okay, I need to check this. Probably the link have changed. So that is old. That is from the COVID. That probably got changed. If the file is big, moving around is not so easy. So this kind of keys became handy. What else I can do here? The copy and paste. Okay, with again with the A and delete. Let me see here. Okay. So let's see what I can do here. Okay, imagine that I want to, let's say, one of those lines to copy. I will delete it. So let's say there are several keys that can help you to select and cut text. There is here the Control K to cut text or an entire line. So if I execute this Control K, it will delete the line. And if I execute this, it will undo this operation. It will uncut the line. There is the escape, in my case, the meta key for selecting, start selecting sections of it. And now you can cut or you can copy. I don't remember the copy because I'm not used to this editor. 6. Okay. Oh, 6 to copy. So escape 6, and you copy width. U control. Let me see. Like this. Oh. Oh yeah. Okay. Yes. With Control U, as in mentioned here, and cut the text. So it's paste Control. Okay. So that's how you move, copy, and the searching capabilities with Control W. Control W. And Control W. And you start searching. And you go to the first place where that is present. So for this, let me see, I will Control X, I will say no. And the first exercise was trying to replicate this code, to write the code. And if you do it, all that you have to do is to compile the code like this. And you execute it like this. And you get the famous cyclic track. Okay, that's one thing. Another thing that is here in the challenges is this exercise. Forget about this. I need to check why if they change the location for this file, or search for another exercise equivalent to this. Is this one? Is a Java code, and so in this case is slightly bigger, but now what I will be trying to do here is to show you how you can use the virtual desktop, one of those virtual desktops, for example, this one. Oh, let me see. Turn the desktop. Okay. And I will be compiling this code and seeing the result on a graphic user interface. Okay. Any questions? I think I will be closing this section here. And I need as much time as I can to devote to the software side. So that's why I decided to rush a little bit on this one. You can read on your own. You can select your own editor and explore. So we'll try to increase here a little bit the quality. I think I can do this. Open the desktop here. And this is another thing that probably I have not mentioned yet. Here on Turnitin, you can open graphic user interfaces, which for some things they're handy. It's good to have. And here I'm working on a compute node. So that's, I'm not really sure if they have more editors here. Probably they have some. Well, they have Emacs. I told you that. Let me see which kind of Emacs is here. Yeah, you see, there is also, for Emacs, there is also a graphic user interface version of that with buttons and all that. It's pretty much the same thing, and the commands work the same way. You can still open, let's say, well, text files. And the commands to leave the view, I just type Control X as Control X C. The commands that are described that to leave the file, they work. So there's just for you to know, if you really, really prefer a graphic user interface text editor, this is what you have to do. You have to open a virtual desktop and start using the tools there. And if you want to see another text editor there, I can make arrangement to install something for you. Okay, you see, they have a bunch of things. So let's go here, versions hands-on, introduction to HPC, the 4 terminal editors, and the next exercise here was with Java. What happens if I use this one? Yes, we will open the graph. Oh yes, yes, it will open this version, the graphic user interface version. One thing, now notice here, this editor gives me coloring. Again, something very nice to have if you are into programming. Or this one also give me coloring. So you see, you have all that, the coloring of the text. And I think the challenge here was to change the C, the constant value for the Julia set. The different Julia set, you can get different sets just by changing the constant here. The usual constant is this, minus 0.7 and 0.27. You start changing those values and you get different motifs for the Julia set. So that's one thing. What I will be doing here is, well, this is VI. I'm leaving this with Control X. Let me see. I demonstrate a little bit VI in the next few minutes. So in VI, if you select VI, which is the editor that I use most of the time, is VI. You go to the very beginning with escape. Escape put you in the command mode. So all the time you are pressing escape. And for moving to the first line, you just put column and 1. And that move you to the top of to the first line, the very beginning of the first line. If you want to go to the end, you press escape and again to put that dollar and the dollar sign. And you go to the end of so the dollar sign means the end in VI, in Vim. And the specific line, if you want to go to the line number 12, you will just put column and then the number line where you are trying to reach. Searching, for example, I want to see where is the word white. So you use the slash and you search, you select that. And if you want to copy and paste, imagine that I want this block to be copied. So again, I'm using here this. If you are in mode, you can use here. I'm now in this case pressing the J, K, L. With the L is like this, the H is like this. In command mode, J and K. So instead of using the arrow keys, I'm moving in the old-fashioned way. And imagine that I would like to copy this section. So what I do is to go into visual mode with V and start selecting the lines that I would like to copy. If I want to delete them to copy in somewhere else, I press D. If I just want to copy them, so put it in memory, I use Y. I move, let's say, to the end of this. Let's see, so I don't damage the code. Let's say, imagine that I want to just put it here. Oh, and for inserting text, if you try to type in command mode, it will not show any text, or will start making gibberish. For inserting text, you need to press I. So that's what I did here. But what I would like to do is to paste here. So it's P. And I paste in the content of that. So I want to delete this. So I escape case, visual mode, and delete. Okay, I would like to go, and this is for leaving the file, to save and leave the editor. And I would like to compile this, to compile the Java code. So I need a Java, because I don't think that it's not by default. So this is something that we will introduce in a few minutes the ways you access code, but I will show you and I will explain this in more detail. So I will be trying to see where I could find in a Java compiler module available. So all those are the modules available. I will explain about modules in a minute. I'm more interested in modules related to languages. And you see here all those. I just want this blank. So I will be loading this module because I would like to use Java for compiling this particular code. And so this one is one particular version of that, of the Java that will give you the Java compiler and the runtime environment, all that. So Java C and is Julia. So I will be compiling that. And in the meantime, okay, let me see. Yeah, I compile it and I execute it. Nice. Not that I would like to do here. And that's the reason why I'm using a graphic user interface, because the program is supposed to make this plot on your screen. And another thing why this is nice to have. Okay, so now let's move on to something else. So now you can read on your own. I skip a lot of section here for especially for Emacs. I didn't did much. I'm moving to the software side, which now we have a couple. What about if we stop for 5 minutes? I drink some water, and I entertain questions from you, and give you also 5 minutes. Let's say we continue at 10 a.m. So it's 9:52. So we continue at 10 a.m. And if you have questions, I will go quickly, drink some water, and we continue, right? Let me see. Oh, it probably is. Yes. Yes, that is my what I mess a little bit with it. So this section here now I think is you are talking about is because I split this section that I did yesterday for. Let me see. Yes, yes, yes. Yes, I broke this. I will fix it. I will fix this. And let me see. Yes, it's broken. The whole thing. This one. Yes, yes. I introduced some changes here on the on this side that make it work differently, because now I changed the numbers here. Is I changed the way I was referring those sections. So I will fix this. I will fix here in the workshop page. But thank you. Yes, I will do that. And I will fix it. So okay, I will drink some water. If you have questions, just write your questions, and uh, I will entertain those questions in a minute. Okay. Let's move on to the next section here. There are a lot of things to mention here in this big section. So let me copy this right here. Okay, so this lesson here and the next one are probably the most important lessons and specific for HPC in this introduction to HPC. It's how you access the software that you need in the cluster and how you submit jobs in the next lesson. Those are the most important things to learn. So that's why I'm devoting a couple of hours to this, to go slow and dedicated for you to know the nuances on the options and all those things related to the software on HPC cluster. So now we have two main clusters with us. This one, Thorny-Flat is one, Dolly Sot is another. GPU-based cluster. All of them, they have different versions of the same operating system. On that operating system, we try to have almost the minimal of software that is needed for that machine to run and for all the compute nodes to run. So we try to be very minimalistic on the software installed natively from the packages of the operating system. That's one thing. Second thing is that we usually exclude there entirely scientific software. So Red Hat will not give you much in terms of scientific software installed from the repositories, from the native software, from the software that they maintain. Scientific software is not included. Another element on the cluster, these kind of systems, Red Hat, those are what we call enterprise level operating systems. So they are very conservative in the terms of the selection of versions and the selection of software that they make available on those systems. They want to be very stable. So if they choose a compiler, they choose an old compiler, old version that has been patched, that has been tested. If for basically all the software in the system, it's usually very old versions of that software with all the security patches involved. But not with new features. No, it's not the bleeding edge of the of software package. And that came with issues when you are working in scientific computing, because in scientific computing, we are really in the leading edge and sometimes in the bleeding edge. So things are half right, half broken, things uses the latest software with the most updated features. So you need those, and we will see in a minute what happens, why we can eventually need newer versions of certain packages or compilers, things like that. So in terms of scientific software, we need to use something else. We cannot use the package from the vendor, from the operating system. We need to install them separately. And sometimes we need to compile them and install them, because the software is scientific software that is released just the sources, and you need to compile that and tweak the software and tune it for the needs or the capabilities of your specific infrastructure for the cluster that you are using. So for offering all that, we rely on three main solutions for offering software to our users. Environment modules, that's one. Content environments and containerization, singularity or obtainer containers. And we will be discussing what is all that and how you can use and search and select the software that you need for your purpose, your needs, your interest. So the first one is environment modules. Environment modules is a way, it's a software package that allow you as a user to switch from one software to another. Enable some software, disable another, and select the software that you want to use, eventually with different versions, and switch that to a different one, just from the command line. And for the administrator to offer to our users, eventually different versions of the same software, and software installed on different locations where you can distribute that software, or we can make available that software for the entire cluster. Otherwise, we will be forced to install the software on every single compute node. And we have more than 170 compute nodes. So we will not be doing that, or it's not the right way of doing it. It's better to have the software installed in one location. There is some uniformity across the cluster in terms of the operating systems, the hardware, so we can install on the head node, and that software will serve the entire cluster. And environment modules is one way of doing that. To understand what an environment module is, we need to go a little bit back and understand what a shell variable is, and what is an environment variable. And so that's what I'm doing here. So the shell, this thing that we learned in the previous lesson, the very beginning, when we started learning the 10 commands, remember the command line. When you are working on the command line, you are working in something called the shell. The shell is also a programming language. So there you can make loops, conditionals, define variables. You can operate with that as you do with almost a normal programming language. It's a programming language with some restriction. Is restricted for very specific purposes, usually manipulating files and executing process on the computer. But still, it's a language where you can write the scripts. And if you can do that, you need a way of storing variables, storing values under certain names, and those are shell variables. So here I am demonstrating how you can create a couple of variables. Those are shell variables. They exist and they are visible for that execution of the shell. So you can do, let me see here if I can do something about this. Oh, no. Let me see, should I do it here? Okay. So let's explore a little bit this. I can define a variable like this. And I can show that variable in the shell. When I want to show the variable, I just have to put a $sign in front of that. And I can do an echo. Remember, the echo is the command to show some text. So the text will be the replacement of the variable I by the content of that variable, and I will do that. In shell, there are some nuances. You can put like this, and if you don't want to interpret that, and we will not be covering shell scripting here, you can use single quotes, and that the variable will not interpret. I can define another variable and I can do some calculation. And I have to remember how this is done. Let's see, right is here. You double the space. Something like this. Okay. Okay. Let me see here. Okay, here. However, those variables that you are defining here, they are not visible for scripts or programs that you run or you execute from that shell. So for making this example here more evident, let me see here. I have something, let me see. Set a, this is how you remove a variable in the shell. I have this, so I have a shell script that is this sum.sh. I wrote this a script, and this script is expecting two variables, a and b, and I will be making the sum of those variables and showing the content of the sum. Imagine that we don't have defined a and b, so you try to execute a. There is nothing. There is nothing here called a. There is nothing here called b. What happens if I try to execute this script? I can execute it like this. It will make an error. It will throw an error because that variable a and b doesn't exist. And of course, when they try to make a sum, it's making the sum of a couple of things that doesn't exist. So it will throw an error there. Now let's try to define a variable like 10, variable b equal 20, and let's try to execute this. Again, this will not work. It's not working because those variables exist in the shell. If I execute this, that exists, but it will not exist inside the script that I wrote. In order to bypass this constraint, I need to convert those variables into environment variables. That means it's like converting a local variable into a global variable, something that is visible more globally, more generally. And you do that with the command export. So I export A, export B. The commands continue to exist. They are there, A and B. But now, if I execute the sum, now that works. Now, inside this, the script, A and B are variables, they exist, and the script can operate with them. So that is the definition of an environment variable. And the shell contains a number of variables inside for all sorts of purposes, and some of them are critical for the operation of the terminal, the shell. And you can see all of them with the command M. Those variables here, there is some that are defined as functions, but look into all this. So all those things that you see here, all those are variables that have been defined. Sometimes the shell use them for certain purposes. Some others are used by Slurm, which is the resource manager, workload manager that we have for submitting jobs. When a job is created, we will see that in the next lesson. A bunch of variables are populated, and the script can use those variables to decide the resources that you are asking, all that. I will just point you to a few of those that are relevant in our discussion, in what we will be talking about for how this operates inside. For example, this one is always there. The home variable, $home, if you want to know the content of the variable. Home will contain your home folder, the folder where you land when you just get into the cluster. That is always there. User is always there. In the case of our clusters, Thorny Flat, Dolly Sots, there is, for example, this variable. This is not a standard, but it's something that we have on our cluster. It's called the scratch. It will point you to the scratch location. Scratch, the scratch folder. This folder where you have like 20 terabytes available for you if you want to use them is this one. While the home folder is limited to just 10 gigabytes. So those are a few environment variables that the shell uses. There are a couple more that are really, really relevant for our discussion. More environment variables that are used to decide where to find commands in or executables in the system. And it's the path variable. So at this moment, this variable will tell you all the places. When you try to execute a command, it will search for all those places to see if it's around, and it will execute it. For example, when you execute the command ls, to see that this is a program. This program, I think, is in right here. If you want to go exactly where it's located, is this one here, /bin ls. You don't need to type the full path /bin ls, because the bin is one of the places in the variable path where it's authorized to search for commands, programs, something that can be executed. Now, if you have this variable path and you can change it, you can add things to it, you can enable new software, new programs that you didn't have at this point. For example, let me see. There is, in this moment, there is no command called abinit. Command not found. It's not there. But there are ways to stick. To load what is called a module, change the content of the path. Now the content of the path will add more things to it. So like locations for the Intel compilers, Intel MPI, some dependencies, and a special location here, right here, where let me see, if I copy this, let me see if I copy this, where the command, the executable or the binary abinit is there. So now that it has been added to my path, now I have the command abinit available. It will not operate, will crash it right now because I don't have input files there. But so that is the whole purpose of environment modules. Give you the ability to enable software, enable, disable, change it, give you access to software by changing a few environment variables that are critical for making certain software visible and to the user. So that is. So let's return here to our discussion. So I told you about the difference of a shell variable and environment variable, what they are related, but they are different. How you see all the variables in the system with the command amp. I was using this small script, the sum, for making a sum and raise you the awareness of the difference between a shell variable and environment variable. I show you a few of the variables that are present on the system. For example, this one, and remember that I show you this, I think, yeah, I show you this, that I have a very colorful, rainbowish kind of prompt. The way I do that, because for me it's important to have, for example, when I execute commands, to know to have these dates, or differentiate if I am on a login node or compute or infrastructure nodes, because I'm connected to multiple infrastructure nodes all the time for administration purposes. So I have some coloring here, and you see that. You see, if I go to in my case, in my way of working, if I am on an infrastructure node, I color those with red. If I am on a compute node, I color them by green. So really quickly, I realize that I'm on one kind of node or another. So I do that by changing a variable in my bash RC, I think. No, in my bash profile. So I have here one environment variable that is this, with this esoteric coding that is basically indicating certain kind of things, like the time from the date, take it with a certain purple. This is the code for purple, and another code here for the username, which is this code here, and the location, the host is a /h. So, and before that, the host color, which is taken from another variable, in this case, just a regular variable, that is tweaking all those things. So this is another way of playing with it, with environment variables, for the purpose of changing how the shell appears to you. So I was using that. And I mentioned this one is very important to decide for the terminal, for the shell, to have a list of locations where you will start trying to find executables, the programs. And if you change those, and that's what modules, environment modules are doing, you can enable one version of this code, or enable a different version, or a different version. Sometimes people uses different versions because some capabilities are enabled or broken on a specific version, but they are okay on another version. That happens a lot in scientific computing. You are working with codes. Some of them has been developed for years, even decades, but some others are relatively new, or they are very dynamically changing, and the behavior is changing. So you need multiple versions. That happens very often, for example, in biology, in people doing genomics, where they have a plethora of codes. It's an entire galaxy of different tiny codes that do different things, alignments, population analysis, all sort of things. So they need ways to switching back and forth between different codes, different versions of those codes, for the kind of research that they are doing. So that path is one of those switches that you can use, or the variables that you can start changing with a module. And this one is pretty much the same thing, but for libraries, where to search for libraries during runtime. And this one is probably less useful for most of you, are the locations for libraries during compile time. That's one way of doing it. Another is explicit during compilation time, to introduce those the location of the libraries. But that's another thing. The point is, the environment modules give you this ability. How you use this? Very simple. Everything is with module something, module list, module, all those commands here, and I will demonstrate those, how you use them. So the first one is to get something clean, module purge. So with this, you remove all the modules on you that you have loaded. If you see which modules you are currently using, you execute module list, nothing. So now abinit, for example, is no longer there. It's not a command. Yeah, you can see, for example, which version of GCC I have is the 4.8. This, by the way, this is Red Hat. This is a Red Hat 7. Turning Flat uses Red Hat 7, which is a very old version of Red Hat. But we cannot change that for various reasons, technical reasons. So we are stuck with this version of GCC. We will see in a minute that we have implications. There are implications we use in that, and how we can bypass those limitations if we move. You load a module with a newer compiler. Okay. So how you load a module, or how you search for a module. So let's see. See all the modules available on the system, and I will be making this big because the list is big. So you see here, all these are a list of modules in the entire cluster. They have grown a lot since the first time we provisioned this machine back in 2019. So people request software from us. We install one version. A few months or years, we need to install a newer version, but we need to keep the old one. So this list is always growing. And we are no longer installing software. The system is old, and it's hard. It's harder and harder to install new software on such old system. And another thing is we have a structure for how we organize the modules on the cluster. So I manage those by tiers. Something that is really low level, for example, compilers, libraries, things like that. Things that you usually only need to compile another software, but they are not the main scientific software that you are planning to use. They are here, the tier 0. So you see here, language under lang, those are programming languages. Under libs, those are libraries. Some codes you need to have certain libraries for various purposes. For example, this one, FFTW. This is for fast Fourier. There is a well-known library for very efficient compute fast Fourier transforms. And there are some other, for example, for dealing with discrete sparse, for sparse matrices. So matrices where the large majority of the values of the big matrices, really big matrices, are zeros. So there are specific, very special algorithms that have been optimized for dealing with sparse linear algebra. And this is one of those libraries that has been developed for that. Let's see. Here, there are some libraries for storing data in binary format. Those are standard libraries. HDFI is a well-known library for storing binary data, like atmospheric data, or things that you are dealing with a large arrays of numbers in hierarchical form. All those. For using parallel programming, distributed parallel computing, right here. And programming languages. So we have, this is the version that we have here. This is the latest version of Python, the C Python 3.11. So we have been moving away from the older versions of Python. So we now support only 3.10, 3.11. And if you have something older, you will use something else that we'll discuss in a minute called conda environments. So all that. So most likely you are not interested in libraries or compilers because you are using directly a very specific scientific software. For that, we have here on tier number 2. And if you are using MATLAB, we have MATLAB 2024 right here. So that's another thing that we are. If you are using Conda, we have Conda here. So this is an intermediate layer, let's say tier number 1. And what you really want to use most of the time is scientific software, directly scientific software for the kind of things that you do. And here, all that software is organized by scientific domains somehow in the tier number 2. So I have here, well, this is a proprietary software for computational fluid dynamics. Next week, my colleague will explain you about a little bit about this. In astronomy, in material science, chemistry domains where we deal with atoms or particles, that sort of thing, are all here in atomistic, at various levels of theory, from the purely classical molecular dynamics level to the electronic structure level. A few codes in bioinformatics. The list here is very small because most people in bioinformatics, they work with conda environments. They're much better served with conda environments. But for a few cases, we have some codes here. Materials engineering are here. Optimization processes, which for business and engineering. So you see all those codes are organized, pretty much served in groups of scientific domains. And finally, here we have various versions of Intel compilers, which are a domain on their own. So we have multiple versions of those. So if you want to see and concentrate on a very specific section, you can use a command like this. Show me all the modules related with languages, programming languages. So those are this is what we get. We get multiple versions of Python, a couple of versions of R, the NVIDIA compilers, Java. We used Java to make this fractal minutes ago, and a couple of versions of GCC, the GNU compiler collection. And that's exactly what we are planning to use right now. So those are the commands for looking for modules. And let's say, imagine that you want to know about one module. So there is module show. If you want to know the internals of a module, atomistic, Avinit, let's say 9.8. This is a description. This is a technical description of the module. So that means that you are changing some variables, some environment variables, like the path. The path will be added at the very beginning, this line. So that is the line that is added, and that is the line that is removed when you unload the module. So that's the beauty of the modules, the environment modules, that allow you to change the path and unchange it to revert back to the original condition. So a few variables that are changed, and a few modules that are preloaded as a condition to load this other module. That is one thing. And we also have like a help for the module. Let me see if I can, which is just a description that we have for most of our modules, which give you a description of what this is all about, which is the purpose of what is having it, what this code is doing, and so you decide, okay, if that's what you want, that this is exactly what you're looking for or not. So now, here I have one case, one exercise, if you like, where I would like to load a set of modules. If the set of modules that I would like to use are compatible to each other, you can load the module. So let's see. Right now I have nothing. Module, yes, I have nothing. What I probably cannot paste here. I don't think this will work. But I just need to pick up. I will be loading. Okay, I will be for a certain code, for a certain execution that I will do it, or simply exploration. I need the latest version of CPython, the Python here. I need to use a little bit of R, so the latest version of R, the 441. And if you see here from the coding of this, I will require to preload GCC 12. So this is what I'm will do. I can do it one by one. For example, GCC 12. And if I look into the list of modules that module list, I have GCC 12 available. I can test it. It's the version 12.2, which is a very recent version, relatively recent version. And can let's see, I can load some other things I need. The Python, CPython 11, and also I want to have the R441. So that will load the modules, and now I can check if I have what I want. So GCC version is 12.12, Python, and this is interesting. If you execute like this, you get Python 2.7. The reason for that is that in this system, Red Hat 7, there is a Python in the system. You can use this command to know which is this Python. In user bin Python, in the very official location or standard location for packages in the system, there is a Python, and that Python takes precedence in the search, and that's an old Python. This is Python 2.7. No scientific code today should be using old versions of Python. This Python has been out of life since January 2020. So it's like a Python pre-COVID. So it's very old. But what we really like to use is Python 3. And this one is 3.11.3. And this is in a very different location. This is in the share location. Python 3. It's in share software line. This is the location. All that software that is in those modules is located in shared software. All the software is there. So that's the version that we want. And the R version is the 441. So if we open our, the R that we are using here is 4.41. And here we have not only R, but we have also, if you are familiar with R, you can see all the packages that has been added to this version of R by default. So we have like a section of packages that we always install, we always offer. And if you want, you can start installing your own packages. Those will be installed just for you. That is the traditional way. I don't have any name of package that out of my head, but this is how you install packages. And something similar happens with Python. If you search here py3 list installed, in Python, there is this command for listing the packages installed. It will throw the list of packages. But what I would like to do while this is executed, okay, is to compile software. So I will be cleaning my environment, purging my environment, not having any version of GCC or anything. I will try to compile a code, and you will see the effect of that. But what is coming? And those are all the packages installed, Python packages attached to this particular version of Python. So the first thing that I will be doing is module purge. So I clean my environment. I don't have anything at all here, no modules loaded. And I will go to my hands-on materials, introduction to HPC and my environment modules. And here you will see this code. It's very small. This code in C++. We can have a look at that. A very small code. What happens if I try to compile this? The compiler for now we have it. Let me see first, which is the version of G++, is 4.8, the old version from 2015. So it's almost 9 years. It's 9 years old at least. And let's see, we can try to compile. I want to compile this code, and it will fail. Okay, error. The reason for this error is that this code, as the name suggests here, uses a specification of the language that is C++ specific 14. The changes have done to the specification from 2014, and the compiler is from 2000, around probably 2015, but those new features of the language have not been implemented by the time this version of the C++ compiler was released. So that's why I have a very good reason to want to see that maybe I'm using a too old compiler, compiler that is very old for the purpose of compiling this code. And this is something that happens a lot in scientific computing. People start using new features, new capabilities, and you need to use C++12, C++17, newer version. And it takes some time for those things to be implemented on newer compilers, at least a couple of years from the specification when you have the documents for those to be implemented. So the thing that I'm doing here is module loading a newer compiler. So if I execute G++ version here, it says 12.2. Now, what happens if I try to compile this now? And in the meantime, I will see. So now I compile this. And well, I will probably skip this, but you can try. You can, like an exercise, you can try to compile it with some of the other compilers that we have. I will show you that. And I can execute this and works. That is okay. So try with the other compilers, the other GCC, to see if that changed anything, and the different module available compiler. Nope. So we have several Intel compilers available. So try one of those, the 2021, 2022, 2023, to see what happens. If you are able to compile, there are a few descriptions here. Or if you try to compile it with all versions, of the language that are here. So we have a very old Intel 2018. I'm not really sure if that is able to compile this code, probably yes. Or the NVIDIA compilers, which are here. So this one is from 2024. So the NVIDIA, which used to be the Portland Group compilers. NVIDIA bought that company. NVIDIA bought is one of the biggest companies in the world, so they buy smaller companies. And they, after some time, they renamed the PGI compilers, which they were very, very popular in the 90s. They were one of the first that offered Fortran 90, the very, very popular compilers in their time. So that now they are integrated into the NVIDIA compiler suite, NVIDIA HPC SDK. So this is another set of compilers that you can try to test this code. Now, with this, that gives you an idea of how you use modules. That's one way of accessing software. So now let's move to another way of using software, which is very commonly used by certain scientific domains, for example, biology, bioinformatics in general, and it's content. But not only bioinformatics. But, so for this, I will clean my environment module. Okay. Well, let's explain and then I will demonstrate. So Conda is another software packages. It's a software open package management and environment management. So it is capable of doing more than just the environment modules, because you can install software. In the environment modules, you install the software is your problem. The installation is your problem. However you put it, you just need to create those modules, and the system will allow you to switch modules. In this case, it combines the environment management, which is setting those variables so the certain software is enabled or disabled on specific locations, and also the ability to install packages that are not restricted to a specific language. That's another good thing, because if you are working with Python and the Python, the code that you want is another Python, but you have pip install, you have that. If you are working with R and the program is in the R repositories, in the CRAN repositories, you can use install package, the name of the package, and the package will be downloaded, compiled, and installed. That. But more generally, Conda will allow you to do that regardless of the language, regardless of the dependencies. It will arrange the dependencies on its own. So it's far more powerful than Conda. And there are two big versions of Conda: Anaconda and Miniconda. Anaconda is something that you can download on your own computer. If you are interested in learning Python, you want a good Python environment for you, and you are using Windows, you can install Anaconda. Anaconda will give you the whole package, the whole thing, well integrated. Many things are installed by default. So you get the Jupyter notebooks, for example, the ability to have your own Jupyter notebooks and run those on your Windows machine or Linux machine or Mac, or whatever. That's one thing. So they install many things by default. So it's a good system if you are working with some scientific computing and you want to work part-time on your own computer and some other time for the real computational demanding stuff and on the cluster. That is a good solution, having Anaconda on your side, and after you translate that into the cluster with Conda. In our case, for the purpose of the cluster, we install a more minimalistic version of that. So it's called Miniconda. Miniconda will not install all those extra packages, but it will give you the bare minimum so people can create their own Conda environments and use them. So that's what we have. We have just the Miniconda. And we have a particular version of Miniconda that receives some optimization in order to search with a better solver for dependencies compared with the original Miniconda. Fact of the matter is, if you want to use Conda, all that you have to do is to module load Conda if you want to know the trick, or if you know it, this is all that is important. So, this environment, I have to copy here, paste here. Okay. This is how you initialize a Conda for you. One thing to notice is that it changes your prompt and adds at the very beginning the name of the Conda environment that you are using at this moment. Okay. You are once you activate Conda, you are always on a Conda environment. Always. The base Conda environment is your first landing place. If Conda is important for you, and I told you many people in bioinformatics, that is reality. You rely on Conda. Thanks to BioConda, thanks to a big repository of bioinformatics packages. Or in other domains, you really want to use Conda, you can add this line to your Basher C. Show you, I don't have it, but if you want to do that, this is Basher C. You just need to add something here, like at the very end. Well, I have some other things here, but you can add it here at the end. So, such as every single time that you log into the cluster, you start with Conda activated. That is a suggestion for those who use Conda a lot. Otherwise, if this is not something that you use that often, you can just play with this. You just activate Conda when you need it. And so everything in Conda is environment modules. Everything is with just one command, module something. Everything here in Conda is Conda something. So Conda and a few arguments, and you do most of the stuff that you. So Conda, if you want to know the environments that are available here, is Conda and list. It will show you the environments for everybody, and also the environments that you own that are in your personal location. So you see, I have a queue here. I was demonstrating this and testing this. So those are my own Conda environments, but those here, forget about those. Those here that start from base here, so all those sections here, this section here up to here. So those in shared software Conda, all those are environments that were centrally installed that you can load. If you execute the command and you don't have any other Conda environments of your own, you only will see this. You will see a star here that tell you, okay, you are right now on this Conda environment. This is one thing. What else is here? Okay, so Conda environments. Okay, this is the command, and here I cut that, I execute Conda mlist, and this is the list of Conda environments current in the system. And you see a few things here in material science, a few here, different versions in, this is bioinformatics, but most people never use those, except for example, genomics. This one here contains like a collection of widely used bioinformatics packages, SAMtools, BAMtools, or BLAST, those are packages are there. So we can have a look at that. Well, genomics, let me see. So what is my current Conda environment? Is base. I will be activating, Genomics 2024. And notice that my prompt have changed. It's changed now. I have the different prefix here, showing me on which conda environment I'm currently using. And now I can see the list of packages in this particular conda environment. You will see, if you are familiar with bioinformatics, you will recognize many of the items in the list. Okay, so this is how you activate the conda environment. And there is the command here, conda deactivate, for deactivate the command, the environment. And now what I will demonstrate is how you create your own environment, which is what most people really want to use. So here, you see the BCF tools. You will see here, let me see, well, I recognize a few here. So Bowtie, for the Bowtie 2 is right here. Blast is here. The BAM tools should be around here. The BED tools, BAM tools, SAM tools. So a certain collection of relatively small, widely known, widely used packages in bioinformatics and genomics, more specifically, are right here. So you load this conda environment and you have access to all of them. But imagine that this is not good enough for you. You have a very specific needs and you want to have your own environment and you want to control it because you don't have control on this. You cannot update the packages here. Those are, let's say, locked to be updated or managed just for system administrators. So you have not control on the aging of these packages. You want your own packages, you want to work on your own terms. You can do that by creating your own conda environments. So this is how you create an environment. I will delete mine because I was doing this earlier. So if you see conda and list, you will see that I have an environment there that is exactly the name that I will be demonstrating. This is another bioinformatics. So I will show you how you remove snow. How you remove an environment that you own. This environment is in my location, is a scheme. Okay, do you want to remove that? Yes, I want to get rid of that environment. Okay, so now if I execute module and list, module conda and list, sorry. Conda. Snowflakes is no longer there, and now I can demonstrate how to create your own conda environment. So I will be using this conda environment, conda create, that dash name, snowflakes, and that is creates an empty environment. We'll have no packages. So conda create dash name, snowflakes. This is how you create a conda environment. In your case, you probably don't have this list of channels. I will discuss about the channels in a minute. What is doing? Oh, yes. This is a good moment to explain this. I cannot do this. Everything that you want to do related to creation of conda environments needs to happen on the login node. Right now, I am using the the virtual desktop because it was easier for me to demonstrate that with the virtual desktop. But here I am on a compute node. Compute node has no access to internet. So of course I cannot install new packages or anything simply because I don't have the internet access that I required for do that. So I need to do it here on a terminal that is on the login node, on a node that has internet access. Module load, so I will do the same thing. Module load conda, I copy the trick. So, and now conda env list, you will see no snowflakes, and now I can create dash name snowflakes, and it will search. Okay, what? Oh, I was doing some experiments here. Oh, we delete this. Okay. Okay. So it says, okay, do you want to create the conda environment on this location? This is the standard location for conda environments, conda envs, blah, 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 and say yes. There are two kinds of conda environments, those defined by name and those defined by path. You can also create conda environments where you decide where to install it, where to create the environment. And there are also, and the procedures for deleting, manipulating those changes if it's a conda environment defined by name or is it defined by path. So, but I will not go into those details at this point. I am just creating conda environments defined with a specific name. It's called snowflakes. It will go to the standard location, has been created. If I ask, okay, what is in there? Conda, so conda activate snowflakes. Now I am on the conda environment called snowflakes. And if I execute this, it will say nothing. The conda environment is empty. I have not installed anything yet. What I will be doing now is to, well, activate it. So you see that the prompt changes accordingly. And now I will install a package. There are packages, and there is one location, for example, in bioinformatics, that is well known. They have like more than 7,000 packages in bioinformatics that is called bioconda. That's why some people in that area of science use extensively conda environments all the time, bioconda. And I will be on the, well, this is the line for creating from the beginning a conda environment with a certain name and attach to it a certain package. I already create this is one way of doing it. What I will be doing is to just install the package once the environment has been created. We can close this. So I am currently in Snowflakes, and I will conda install using the channel bioconda. So try to search for that, a package called biopython. Before that, I would like to search. Let me see if this works. I know the name of the package. I don't know if it's available on bioconda and which versions are available. I want to answer that question first. So that's will probably take, I want to know which are the versions available on bioconda before deciding if I want the latest version or if I want very specific version of that. So you see the list is extensive. You see here different versions and different builds. Builds means it's the same version, but potentially with different dependencies. Newer, compiled with newer libraries, despite of the code BioPython being of a certain version, the people who prepare those builds could have decided to use, for example, different versions of Python that is kind of encoded here. So some of them were compiled with Python 3.6, and some other here was compiled with the older Python 2.7. Though those are very old versions. If you go here, is less evident here. So you see here the same BioPython, for example, compiled with Python 3.10, 3.11, 3.12. So that will change the dependencies accordingly. So imagine that I want to be sure, I want to use the Python, but the BioPython 1.8 compiled with Python 3.12. I want to be very specific. I know if you want to do that, what you have to do is to put here install version, and you say equal 1.84 equal this. Oh, what I did. What to do everything again. Oh, okay. Is this one. That is the version that I want. So conda install this version, this build, and that's how you do it. You can decide just the version, and the conda will decide the specific build. That could trick you if you sometimes this is good to be very specific, because sometimes it will pick the version based on alphabetic ordering of the builds. Will be the last in the alphabetic, which in this case I think will try to pick the pi 3.9 instead of the pi 3.12. So now that is the solution for the dependency tree. It will pick this Python, this version, this build, and of course that package will bring some other dependencies. This package was compiled or was constructed on top of some other packages that are doing libraries and things like that. So there is a big chunk of libraries here. Linear algebra, some Fortran stuff, OpenBlast stuff, a bunch of stuff here. And also the Python version. The Python version you see here, of course, is the Python 3.12. And that will bring also different versions of NumPy, some other Python tools here to get this as a coherent set of packages. I will say, yes, I would like to, I agree with that selection. I want that version of BioPython. And it will start downloading all those packages and building my environment for my usage. This environment is only for you. It will be on your home folder. And I will show you a trick that happens when you do this too often. So it will. Okay, in the meantime, I can discuss it. So here I was going much simpler with this. I select BioPython, but I didn't make any choice on the version. And at the time when I did this, the version that was picked was the 1.70. Notice that now it's 1.78. And this one was with Python 3.6. And so here, well, here I took, and some of those packages were probably already installed. So install Python 3.6. Today is old, but so it will, you say yes, no, you say yes, it will start preparing the packages, download those that are missing that you don't have yet downloaded, install those, and at the end of the day, you will have something like this. The system now, if you see the conda list, you will see the list of packages on these snowflakes conda environment. This is the list of packages. Now, you can try to install multiple packages, for example, for a project. At certain point, that start being less and less convenient. So you will add more packages, and that's probably fine. They will just add the package. You start adding too many packages to the same code environment, and you start colliding in dependencies. So sometimes that is still solvable by downgrading some dependencies. So installing an older version or a newer version. So making arrangement of the package. Some other times the differences between dependencies so big that you can no longer install a package on the same conda environment. Solution: having multiple conda environments, and you switch between them for the different steps in your execution, or the steps that you need for processing the data that you need. So that's why the suggestion is try to keep the number of packages on a single conda environment relatively small. Try to be compact and keep a coherent, reasonable size set of packages. Now, here I am demonstrating, this is this is no longer too really important. When I first wrote this, the versions that we need still to support Python 2.7 or something. We still have it here. If you see the conda env list, we have here Python 2.7. For someone wanting to execute something with Python 2.7, the poor guy was unlucky, and they got Python 2.7 code from the supervisor, and they need to run something. So that's one way. You activate this Python 2.7 and you try to execute that. Many times things are broken on some other levels, but that's another problem. So that's one way of using Python 2.7. We do no longer have modules for that, for Python 2.7 on the system, but you can create your own. If you want, you can create your own conda environment with Python plugins. Okay, so what else I'm doing here? Searching. I already show you that how you search in Bioconda, for example, versions of a package. I show you the different versions of Bioconda, different versions of NKL, some other things. And let's try to rush this section here. And not many people need this, but there are ways to create or to write the recipe for creating a specific Conda environment. And you can be very granular on that. You just need to write a text file that contains the prescription of the packages that you want to see on the Conda environment, on a given Conda environment. This is handy, for example, if you are working with collaborators in some other universities, in some other places, some different departments, something. And you want to have a common ground to be on the same page with the Conda environment. So you give them the recipe for the environment, and you agree that all the participants of the collaboration will be working on the same Conda environment with the same versions, such that they can reproduce the results. Whatever is done by one member of the team can be reproduced by another, simply because they will be working on the same Conda environment with the same. This is one way of doing this, where you are not deciding the versions, but you can also be very, very specific on certain versions, certain builds, and create like a description of to the details of a Conda environment. So one way of doing this is, let me see here. Well, here is in a small example. I have a few examples here where I am declaring the environment. And here, if I use this command, in this case, I am creating an environment with a path instead of deciding the location, not the name. This is an alternative of doing that, using the YAML file for recreating the environment. So that's, and after that, I activate the environment, I list the environment, and you see all the packages there. This is kind of anachronistic because you still don't know how to submit jobs. But here I am describing. We will probably see this in more detail when next lesson. This is how you write the submission script. For example, for executing bow tie. So I have my Conda environment, and in my submission script, this script will activate Conda, will activate my Conda environment, will execute the code that I want, bow tie 2, for doing something there. And after deactivate, I could change the Conda environment, do something else, and after doing something else, and I finish with that. And this is how you remove the Conda environment. I show you how I remove my Conda environment with my name. And this is an alternative for deleting a Conda environment that was defined by a path, by a location. So you say delete the Conda environment located in this place. Or if it's by name, is with this command here. Okay. There are more documentation about this, some other things that you can look into. If you want, nothing prevents you from installing your own mini Conda if you want on the cluster. Some people do that. They want their own mini Conda, they want to work on their own terms. It's up to them. You can do that. Or you can simply use what we offer. There is just one small thing that I would like to mention here, is that it's often the case that when you start creating those Conda environments, you fill your quota. And my quota is quite used. So it will not be possible for me to have all what I have in my conda environment. So my conda is actually a symbolic link to a location of my scratch. And I suggest this for our users to do. And so if you notice that you really want to use conda, don't keep your conda, your folder .conda in your home folder. Instead, move the .conda to the scratch and you create a symbolic link. At that moment, if you go to your .conda folder, and if, for example, I check the space that I'm taking on my .conda folder, I don't know, it will take a few seconds to give me the answer, but it's big. So it's not possible for me to have my .conda folder. It's 4.1 gigabytes. So, and some people could have 8 gigabytes. So right now I am using 8 gigabytes on my home folder. It's better for me to keep my .conda folder out. The .conda folder contains basically two things: the environments themselves, which are here. I just have the snowflakes, and I was trying to do something with R, so I create a conda environment for testing something on R. And here I have the packages. So all the packages that I was downloading when I was demonstrating the snowflakes, the bioconda, all those packages land here. You can delete that if you want. No problem with that. You can delete all those packages, because those are the installers, if you like. If the next time you want to recreate a new conda environment, the package will not be there. You need to download it again. But that's the only penalty doing that, is that the package need to be downloaded once again. So now let's move to Singularity containers, which is our third venue for accessing software on the cluster. Singularity containerization is a term for isolating the file system or from operating system on a file or on a folder. So it's an isolation way, path for keeping software self-consistent and independent from the host, from the file system of the host to a certain degree. And there are two solutions related to this. And it's important to make the difference at this point. Containers are not virtual machines. Virtual machines are another way of emulating the hardware of a machine. So you are running, for example, a Windows machine or a Linux machine, and more likely this is scenario. You have a Linux machine, and you want to use Windows. And Windows is a completely different operating system. So what you use is a virtual machine in that case. A virtual machine that it will emulate the hardware such that you can install Windows there, and after packages that work on top of Windows. A container is a different thing. It's just the file system. In this case, we are talking about using the file system from a different Linux distribution or a different version of the same Linux distribution. But at the end of the day, you continue to execute Linux inside. How we use, or why you use containers? Basically two reasons. Packages that have a lot of dependencies, or the dependencies are complex, and conda is not a good fit for them. That's one option. That is the case, for example, for codes in machine learning, deep learning, codes in artificial intelligence, PyTorch, TensorFlow, those deep learning frameworks for training neural networks, we usually prefer to containerize those. So you have the software, the dependencies, and we add more things to that. For example, extra Python packages for manipulating images. Build is there. Some facilities for monitoring the changes on the wakes, biases, all those sort of things is much easier to maintain and to offer that kind of software containerized. That's one solution. Another situation where we use containers instead of conda environments or modules is cases where the software uses graphic user interfaces. So I probably we have one example down below where that is the case. And let me see. Well, I delete that. That was showing you after I delete. Oh, going back to that. Now the conda, my dot conda is small, but still. So let's see. Now 2.3 here. So now conda. Now let's move to singularity containers. All those singularity containers are here in the folder shared containers. All those with the extension SIF are singularity images. Okay. There are different solutions for containerization. One of them that is widely popular and people sometimes heard about those are Docker containers. The reason why we cannot use Docker containers is because those are meant to be used by users who has super user capabilities on the machine, and we cannot offer you that. So singularity containers is a solution tailored for HPC systems where our users want to use containers, but they do not have the administrative permissions that are required if they try to use a Docker container. And you can use a Docker container to recreate a singularity container. So there are ways to transfer things from one side to the other. Singularity changed name relatively recently, and now it's called Apptainer. So on some of our newer clusters, on Dolly, the same thing is called Apptainer. There are symbolic links and to still use the word singularity if you want, but keep in mind that those two things are the same thing. So just due to licensing, and they move into a private, like a private software entity. They are changing names. So the free version, the version that people use on HPC cluster, now is called Apptainer, Apptainer. But it's the same thing as Singularity, uses the same commands, the internals are pretty much the same. So just keep in mind that those two names are there. And in the other cluster, in the HIPAA compliant cluster, is also Apptainer. So eventually we will be installing the newer versions Apptainer everywhere, and we will shift out the name for Singularity to Apptainer. So let's see what we have here. So let's review a little bit the kind of Singularity images. So those files here are called Singularity images. Those is one file that has compressed, so it's an archive of an entire file system, an entire Linux file system. Sometimes Ubuntu, so you see some of them are Ubuntu based. So even if the specific distribution that we are using in the cluster is a Red Hat, it's called Red Hat. This is a enterprise level distribution for Linux. Some of those packages naturally offer installers or instructions for Ubuntu systems. So we create the image for them on top of Ubuntu, and we are happy with that. So a quick review of the kind of things that we have. We have a few images here for bioinformatics. This is pretty much the same that we did for Conda, the Genomics 2024. But here we add more stuff. We have some other extra packages that were complex enough, so we could not offer them via Conda, but now we are offering those via a container. That is one here. All those that start with NGC, NVIDIA offer something called the NGC collection. That is a collection of containers, originally Docker containers. But what we do is to take the containers from them, so the recipes for building those containers, optimize for NVIDIA GPUs. So all this software uses GPUs somehow. And we have a few GPUs on Thorny. That's why we have those. And on Dolly, this is the usual way of accessing software on Dolly, is to use containerization and using the NGC containers. So we take those containers from the Docker recipes, we convert them into Singularity containers, and I add extra packages to them. So I add more functionality, people, and things that I notice people request often from PyTorch, for PyTorch, for TensorFlow. I just insert those things inside the container. That's why you see here those. And often I update those. So you notice here, this is from 2023, but now I am offering the 2024 6 version of those, which is really recent versions of PyTorch, for example. So NGCs are usually deep learning stuff or molecular dynamics codes, NAMD, LAMS, GROMACS. Those are packages for classical molecular dynamics that run very, very efficiently on GPUs. So we have those there for our users. A few other packages, a few versions of RStudio, for example. For those, when you execute this, when you go here and you try to open RStudio here, we have the list of versions of RStudio here. What you are doing behind curtains is selecting one of those Singularity images. If you want 441 here and you want to launch, see here, it will take a few seconds. Using RStudio, you are actually selecting one of those here, one of those containers here, 2023 for 4.2, 4.3, 4.4 versions of that were integrated on top of a basic layer of Ubuntu with different versions of Ubuntu, Bionic or Yami. So we try to use the latest version of those. So that's what is happening. So we are using containers, even if people use containers, even if you are not aware of them. Behind curtains, we use containerization a lot. A few others with Tornifla, with TensorFlow, sorry. And that's it. A few other things in mathematics. Those are the containerizations, the containers that we use. So how you use a Singularity image? Well, that description is relatively old. Here, this is something that we will see next lesson about submitting jobs, interactive jobs. What I will be doing here, and this is how you submit jobs, how you write a submission script. What I will be doing here is something else, something that is very, very important for many people, is you want to install packages for being used inside a container. For example, here, let's say, well, this is for RStudio. If you create an RStudio session, this is what you do. You are internally, you are using a container for R4.41. And the other example that I would like to show you is here. Imagine that I would like to use a Singularity container here for PyTorch, and I want to use another software package that is not there. So I would like to install another package. And so you cannot do that from the container running on a compute node. So you cannot install software here. Install software here will not work because you are on a machine that has no internet connection. You will not be able to execute that from a Jupyter notebook because that Jupyter notebook is running on a compute node that has no internet connection. So what I will be demonstrating is how you do that when you don't have, when you need to install a package. So the first thing is to load Singularity. Okay. And I want to get a shell inside a container. So notice that I'm on I'm the login node. So this machine has internet connection. So I can install software. Singularity shell and the name of the container. I will be using one of those NGC PyTorch 2406, for example. So here I am getting a shell, so inside the container. So if you see here, this file system that you are looking here, this is the file system. Actually, I think it's an Ubuntu machine. So you have APT, yeah. This is an Ubuntu machine. NVIDIA creates those on top of Ubuntu. And I want to install a package from it. So I can install a package. I don't know which package because I was trying this one, but this one already I have. I probably will say that I have this package already because I was testing before with this. Yeah, it's already there. But I can remove it. Well, yeah, I can remove that. Or let me see, I can search for something else. Well, I can remove this because this is a package that I own. Oh, pip uninstall. Yes. So notice when you install packages, you are installing packages on your home folder. So those are locations where you can write. I need the Singularity container to access the functionality of Python that I want to use inside the container. So now if I try to install that, I will say, okay, I am installing this package, for example, and I have it ready here. So now that I did that, I can open a Jupyter notebook and the package is there. So this is not, but if I execute this here, this package is in the list of packages. It's right here. So this is how you install packages for you using a container as a middleman, if you like. In the case of R, for example, it's pretty much the same thing. Now I will be leaving this Singularity container for probably open a new session here. So in the case of R, you need a package for R that you don't see it on the list of available packages. So what you do is module load singularity. You get a shell in the particular container for RStudio Studio 2023 12 for Python 4.4.1. And you open the terminal-based version of R. Let me see if I can find something installed. Packages. I think there is something with the same name. At that moment, you can install. I'm not really sure if such package exists. I need to search in CRAN. But that's the way you can install. So many people do that. Let me see. Okay, so I will demonstrate that. And a few other things to mention here. Well, there are ways. Today, not many people use this, so I move it just to be mentioned if I have time. To create private repositories for you or your group, and we can make arrangements for that. Especially groups, research groups that have some involvement with development. They could have their own repository and of modules that they own and control. That's something you just need to add a new extra variable in your Bash or C, adding to the module path this environment variable pointing to a location where you want to create your own set of modules. And module files are just text files. You can pick one of the modules that we have and adapt it to your purpose. That's one thing. Another thing is create new images, for example, in Singularity. You can do that. Sometimes it depends. I think in Dolly it's possible now. You can create your own images on the cluster. More often, what people do is they create their own images for Singularity from Docker containers on another machine. They have another machine in their labs, they create the images, and they transfer the images back to the cluster or the clusters. So that's here. What I'm describing is a very small example of how you can create a image and how you can build the image with this command. We'll see if I have some time. Maybe I have time to demonstrate that. Or if I want to use this, let's see if I can demonstrate this. So here, let me see, this one is not working. Install package. It's not working. No, let's skip it. Let's close this. And let's okay. Close this. Let me make some space here for cleaning my interactive sessions. I will not using this. And not this. And not this. Okay, so I will go here and show you. I am a normal user. I have here a copy of that. CD workshop hands-on, CD function HPC. And here I have 4 and 11. I have one example of a container. The example is relatively old. CentOS is no longer developed, but so you can replace that for Rocky. Let's see if that give me an opportunity to move that. I will see if I can reframe that. Is CentOS.bst for a Rocky definition file. So let's see if I can do this. So Rocky is another Linux distribution, binary compatible with Red Hat. That is like the successor of CentOS. Rocky Linux, Alma Linux, those are free versions of Red Hat Enterprise Linux, which is not free. Well, I don't need this anymore. Let me see. I will click. This is good enough. So this is a very minimal definition file for Singularity. So what I will be doing, Singularity, build sandbox. Sandbox, okay. This is the command line in general for building Singularity build to create a new Singularity image. This is kind of advanced. If you don't plan to use Singularity containerization, it's okay. This only serves some niche set of our users. This is kind of advanced, so that's why I'm moving it to this position in time for the lesson. What I'm doing here is Rocky. Is I will be creating a Singularity container. How is a question mark if I am able to do this on Thornyflat. It used not to be the case. But you can do this. Yeah, you need to be root for that. On newer clusters, I think in Dolly, I can do this. So what people do is they follow this prescription on their own computer, another computer. Build the Singularity container. So I will have to do it. If I want to demonstrate this for real, I need to become root. Because at that time, being super user, being root, or having administrative capabilities was a need for building the container, not for using it, for building it. So I will be demonstrating. And on Thorny, we have several limitations on that. Workshop, hands-on, introduction, HPC. Okay. So we have Rocky, and I would like to know if I can build this. Module load Singularity. And Singularity build sandbox. Rocky. What I did? I cannot. Oh, it's asking. Okay, I cannot do that. But and CentOS final. Okay, for CentOS is still good. So here is how you build a container. So with this command that is described here. So here, the exercise, the idea of the exercise is I was creating a container. I was inserting a certain libraries and a program that requires graphic user interface. So I was creating the image with all the graphic user interface library, GTK or Qt. I don't remember exactly which were the libraries. I need the compiler and I need these extra libraries that will bring a whole set of dependencies to them. And at the end of the day, I will be creating the software that I want inside this containerization, and I could run it with no problem on the computer, on the cluster, and the instructions were here. I will prefer not to go to that here, and I just want to entertain questions or go deeper into something that people want to see here for these three things. So the environment modules, conda environments, and singularity containers. And also, if I go, for example, here, let me see. Let's do this. On demand DS. This is how you access the other cluster. Open on demand for Dolly, just to show you the kind of things that we have. Because here, this cluster is a GPU-based cluster. We have a bunch of codes and versions of Singular. Everything is our containers are here for different versions of them. So that's one thing. And you can decide how many GPUs do you want to use and all that. The reason why this is interesting is in Dolly, this is the shell for Dolly, module load. It's still called Singularity. Yeah, you have here many containers here, all those here are containers, not only for deep learning, but also a few for electronic structure, for molecular dynamics. They are here. People use those kind of things. And singularity here. Singularity here. Let me see. Container is here. Oh, yeah. This is what I told. The new name for singularity, for what used to be singularity, is obtainer. So the commands are exactly the same. Build, shell, exec, all those commands are there. What we will be transitioning from singularity and on our workshops, phasing that out and concentrate with the new name that HPC clusters around the world are now using, this obtainer. And so let's see. Let's make some exercises here. So singularity exec, singularity shell, well, share container, for example, NGC. Let me see what is here. No, better. NGC, for example, PyTorch, NGC, PyTorch 6. So with this, you get a shell inside the container. This is one thing. When you execute this on a submission script, or you want just to execute a Python code or something, a Python script, instead of getting into the shell, what you do is this. For example, Python 3. I don't have any script to execute. I can just ask to look into which is the version of the Python that I have inside, or I can see if I have IPython there. IPython. I want to execute IPython inside the container, and this is how you use it. And some containers This is like they have their own capability to run executions on their own. So they have like a predefined execution. I don't think that this will have it. I'm not really sure if this have such thing. So there is another command here for run. Let me see what it does. Okay, it's just getting a shell inside PyTorch. So those are the commands, the main commands in Singularity. Singularity. You can see all of them with that shell. What people more often uses is the shell, of course, the exec, the build for those building new containers. Some people can introduce tests inside the container for testing that they work after building. So there is a test. There is this. If you want to know the details of a container, especially for those that came from someone else, you are not, is inspect. It will show all the metadata for that. For that container, from which Docker was created. So, and the name of the Docker container. In this case, the recipe for building this came from NVIDIA. We took that, we convert from the Docker recipe into a Singularity container, and after we add more things to that. So if you see more stuff here, I think you can access the recipe here. Is okay, all. So you can check how all this was created. Oh, not very nice way, in a JSON way, but this is the content, the real content. Cat. This is the definition part. This is the recipe for creating this. Again, people also uses this strategy for collaborations. People use the same software. Many HPC clusters, big one, small, use Singularity containers, so they have Singularities somewhere. And people can agree on using the same container for a certain research, for a certain project. They share the recipe, or they share the image itself, and on the different clusters, they can run the same execution, and they should get exactly the same results. That's another thing that is interesting to use with this for reproducible science. So if you have any questions, we have a couple of minutes. Otherwise, we see each other if you are attending for the Python session this afternoon. Otherwise, next session here for the introduction to HPC will be next week, Wednesday, and this one, the scaling of jobs, which is another big chunk of thing. And a little bit, so I will devote most of the time to the scaling of jobs, and a little bit less about the terminal multiplexing, which is something that allow me to have multiple terminals and keep those terminals alive, even if I right now close this computer and I'll move somewhere else. I can regain all my execution. So for power users, people who use this, the cluster extensively, is something that is very valuable to know about terminal multiplexing. Yeah. And in the next Friday, I will use all that we learn about conda environments, Singularity containers, the team mocks, the jobs, to present a few examples related to machine learning and deep learning. So that will be like the practical use of all what we have learned these days in that context. And in the afternoon sessions, my colleague Irene will explain about codes that are connected through the use of partial differential equations. So computational fluid dynamics are codes that solve the Navier equations, for example. In general relativity, there are codes that are solving the equivalent equations. In magnitude hydrodynamics, all those things, at the end of the day, those are partial differential equations that you need to solve, and there are packages for that. So using this common theme, my colleague will present you with that, with how you use those software, how you connect that and make use of them in the HPC cluster. So with this, we are closing for today, and see you this afternoon or see you next Wednesday, depending on you. Thank you very much. And again, yes, I will fix this. I messed with this. So for the workshop, all these links are broken. I need to change all that. But I will do that. I will do over the weekend, and you should have. Yeah. By the way, I keep this. So if you want to use this, I'm not planning to. I'm planning to add materials for the next week and all that. But we never remove the workshops. So in a few months, if you want to return to this, you can have it. You can access all those. Thank you very much. We have 9 people today. Not bad.